Hello everyone, welcome to Fractional Excitations, the podcast from Tafti Lab at Boston College. The purpose of Fractional Excitations is to know about human aspects of our research. The research we do is called quantum materials. And my name is Sudaman Balguri. This is Enrique Gonzalez. We are grad students from Tafti Lab, and here is Grace Naugle. She's an undergrad she's a senior undergrad in Tafti Lab, and she will be graduating in the following weeks. And now we will talk more about her research and get to know about some aspects about some struggles that she faced during this research. And welcome everyone. Hi Grace, hi Enrique.
Hi.
And let's start the podcast. And so when I first know you, Grace, when we first joined the lab and when we know each other, I know you are from chemistry department, but right now you are a full-fledged physicist.
Yeah.
Going into do research, PhD in physics actually.
Yeah.
So tell me more about this transition.
It was a bit of like a circuitous path. I started in chemistry. I really liked modeling things. I was curious about the world and wanted to understand how the world worked, and chemistry provided this way to kind of get at how do really small things work. And I really liked that part of it. But I realized after taking, it was mainly organic chemistry and chemical biology, that my brain was not wired to memorize such vast quantities of information, and I really missed the mathematical side that physics kind of has. I was taking other classes that allowed you to model phenomena with math and realized I really wanted to do that, but I wanted to do that with the natural world, not necessarily people. So that kind of led me to start considering physics, and I was able to make the switch kind of throughout my junior year. It was kind of a gradual transition, but by the fall of my senior year, I was a full-fledged physicist, and I really haven't looked back. I'm really happy with it.
No, that's good. Actually, I also it's a personal connect with me too, because I did shift from engineering, mechanical engineering in undergrad to physics, and the reason for transition is again similar. At the underlining, it's always physics. So chemistry is an advanced topic which is built upon physics, and so is engineering.
Yeah.
I think you said the reason was you wanted to learn more about particles rather than people. So that's people is more towards chemistry side and particles is more.
Yeah, no, it was more fundamental than chemistry
Right.
ever be. It actually answered the questions, rather than chemistry. It was more about like making something or getting a reaction to go.
Yeah, that's good. In fact, we were in our office. Me and Enrique, we were all not even discussing. We were arguing about how life came into existence, and we got to know that the answer to that shouldn't be biological; it should be physical, because biology comes from physics.
Yes,
and we got to know the answer is entropy.
Yeah.
That's why we wanted to reproduce. That's why we want to keep this do whatever.
I before was not a big fan of chemistry, but in our lab we use a lot of chemistry, and I now feel that it's very useful and it's very interesting. And I go into this because, of course, you come from chemistry, you come with a tool set that you can actually use in our lab. So I can see how you ended up in our lab, but can you talk to us a little bit about that, and actually what type of things you use from what you learned in chemistry in our lab?
Yeah, so I'd say it was kind of after my sophomore year. I'd been doing some theoretical chemistry research, and realized at that point what I was learning was basically physics, and not sure what I wanted to do, find a lab that was kind of in the middle. And Tafti Lab was really the only lab that had opportunities for both physics and chemistry, and I could kind of dabble in both. So that's what excited me, and that's kind of what drew me in. I think the main things I take from chemistry is it prepares you really well with different lab schools and just troubleshooting in the lab. You're comfortable with a lot of different glassware and whatever, a lot of different techniques, and you're used to having to like learn on the fly and troubleshoot the reaction's not going the way you want, or the synthesis isn't working. Okay, why did it go wrong? What experimental error could I have potentially inflicted this with? And I think the other thing is you're used to having, I know Nate talked about this too, but using your chemical intuition. I think the chemistry department trains you really well in knowing, like, you could rigorously solve this out, but you could also take a really smart guess. And so you're basically trained to guess at things really well. And I would say that really helped with designing synthesis conditions and just thinking through, okay, I don't want to do a million different trials. How can I kind of narrow it down? So I think chemistry really helps kind of with the practical day-to-day, the lab skills, and just being comfortable and confident in the lab.
Makes sense. One thing I can know about chemistry is that you have a better safety rules.
So it goes
that
both ways.
Goes
Chemists
both
can be
ways?
scary.
Oh, okay.
Chemists aren't afraid of a lot of.
Aren't afraid, so yeah, they do some stuff that we are afraid more, but our rules are set
Yeah.
and your rules are already high.
So you were mentioning about how you use the intuition in our lab to synthesize different materials. So for our viewers, what is done in Tafti Lab is that we use chemistry and physics for making different materials that could be interesting and can show different physical phenomena that we want to study. And so we find these materials, we try to make them using chemistry, and then we probe their physical properties. Now let's talk about what you've actually done. So what are some of the materials that you've grown and studied, or what are some of the interesting things that you've done that you believe you've done in Tafti Lab?
Yeah, of course. So at kind of a broad level, I work on fluctuating magnetism. And so I've been taking compounds that have shown interesting magnetic properties and performing what's called a topotactic reaction on them. And so that allows us to create new materials because we're kinetically stabilizing these metastable compounds. So the first system I worked on was actually the work of a previous undergraduate chemist. I was able to be trained by her, so that was really cool. And it's this interesting monoclinic compound it's an interesting compound because it changes color. So that's your first sign that like you chemically tuned something, and then when we did measurements on it, you were actually able to see the lattice parameters change in accordance with the chemistry we had done. So that's a really neat system, and that's the one that I started on. And then kind of this year I've transitioned to working on a different system. Again, it's a magnetically frustrated parent compound, which has really interesting magnetic properties. And then I worked on figuring out a synthesis condition so that we can make a large quantity of this material, which we actually just finished today for a neutron scattering experiment.
Nice. This is good. So now you're going into doing some neutron scattering experiments on these materials. What do you want to find from this?
I think for the first system I talked about, we're interested in the chemical composition because lithium's really light, so it's hard to see with X-ray, and also the magnetic ground state. So neutrons interact magnetically with your sample, so you can get information about the magnetism. For the second system, that one I'm really curious to see what the magnetic ground state is. I think that will be a really cool project.
Yeah, that's nice. As far as my experience goes with the past people or the previous members of our lab, I feel that the line of your research, which is spin liquids, it's theoretically very challenging. We'll go into that part later. Like people don't even know how to exactly define a spin liquid or at least find a spin liquid. But the growth of the spin liquid is equivalently difficult. And I know that sometimes when another grad student in our lab, when she grows something, it's so susceptible to the humidity in the lab, so that we have to change the humidity, and everyone suffers from the hot climate. So I'm sure you also faced many such issues. You can share some of them.
Yeah, so for the first kind of project I talked about, getting the parent compound to replicate is really hard. You could chalk it up to the temperature, the humidity, like the amount of excess you add, all those things. The furnace, we basically have like a little monopoly on one furnace because it just consistently works in this furnace for no great reason. So things like that, you're constantly kind of tuning those parameters and trying to hold things constant through each trial, but obviously we're experimentalists, that's really hard to do. So that was kind of the challenge there, and then the exchange or the topotactic reaction, that was probably actually the easier one of the two. Once we figured out what salt to use, it was pretty robust. So that was actually nice. With the second one, it worked. It exchanged well. We just have a lot of impurities. So we were, again, tuning the different parameters, trying different temperatures, trying different amounts of excess to see if we could reduce the impurities. And we're hoping the ones we have aren't too bad. So we have one that's not magnetic. So hopefully that won't interfere with any magnetic measurements. But that was the challenge of, is there a way we can chemically remove these impurities and they're not super soluble in common solvents, so we're a little bit stuck there, but things can just be sensitive.
How do you know you have these impurities, or if you have the parent compound? And also you mentioned that if a sample is magnetic or not. How do you how do you know these things about your samples?
So the first thing we do, I think, across the board in Tafti Lab is once you make a material, you X-ray it. So we compare the X-ray patterns to previous samples to see, like, is it replicating? Is it consistent? And then we can compare it to the online database of previous X-ray patterns to see what potential impurities are present or what is the main phase that we have. The other thing we do in our lab is magnetization measurements, so that gives us some insight into the magnetic properties and the transitional temperatures present in these materials.
Yes.
So before you also mentioned that you saw a change in lattice parameters when you changed your recipe for the material. And how did you see these changes? Was it also an X-ray, and how do you differentiate them?
Yeah. So you can tell on the X-ray. So we're interested in what's called the C-axis peak. So it's like the distance between the two layers in my material, and you can tell if that interlayer distance has changed based on where that C-axis peak is on the X-ray. So we were kind of tracking that to see, like, that was our first indication beyond the color that lithium was now in my sample instead of sodium.
And the X-ray part is really tricky because there are different pucks of X-rays that we use with different amount of depth, and you have to use the same puck in the same slot so that you are extremely accurate, and then you get to know that what's the actual difference from coming from the sample or from the instrument. Right?
Yeah.
And which number puck did you use?
We use size 11,
Size
position
11, yeah.
1 on the X-ray.
And I always use slot 2. That's my slot.
Yeah. I accidentally picked 1. I wasn't thinking when I did it, and now I'm like stuck forever with that one. But
So you work with general ideas of quantum spin liquids, which are, as you said, frustrated. And what does that mean, the frustration part?
frustrated means that there's multiple interactions that can't simultaneously be satisfied. So one easy way to think about it is to imagine an equilateral triangle, and then on each corner you have what we would call a spin. So one corner could be spin up, the next could be spin down, and then if you want to create this alternating pattern, that third one is stuck fluctuating around. So there's no way for this to be simultaneously satisfied unless the spins cant out 120 degrees. But that's the basics of frustration. That's not like the best model for hosting a quantum spin liquid, but there's other models out there, and I think it's, interesting physics.
No, it's quite interesting because then it stays in two states at the same time, and that's how you don't get an magnetic ground state.
Yeah.
That's the spin liquid.
Or you don't see it.
It's like a liquid. There is no solid magnetic order.
It's long range and tangle, so there are well-defined magnetic.
Yeah, but there's no magnetic order.
It's a paramagnetic.
Yeah,
like
they're strongly
state.
correlated, but they're strongly entangled, but there's no order.
Yeah.
And like, how long usually were your synthesis? Like, how many days was the synthesis?
So the first one, do you mean like including the precursor or just like the exchange?
Oh, you have precursor too?
Yeah, you have to make the parent compound and then you have
Run
to
us through the whole
exchange it.
synthesis.
Yeah, so to make my
What is it?
materials, first you have to make the parent compound. So for the first system, that takes like a day and a half kind of total. And then you do the exchange reaction, that takes like another day and a half. So you're probably done in 3 to 4 days, maybe 5 if you include a day for washing and you do it all sequentially. And I'd say that's probably, or no. For the second system, the parent compound takes a week to make. So that's a little bit more time consuming, but then the exchange takes the same amount of time. However, we can make a lot more parent compound. Like we can make 1 gram of parent compound. So it's a trade-off, but it's not too long.
And so what are these hands-on things that you're doing to actually fabricate this sample?
Yeah, tell us more about the fun part or even the adventurous part that you do where you actually melt the glass.
Yeah,
and
so
make those tubes.
the exchange, we don't want it to react with like the outside atmosphere or oxygen. So we go in the glove box, we grind our powders together, we put it in a crucible, we put it in a glass, basically test tube, and then we take it over to a torch and we seal it. So we heat it up and put it under vacuum and then close it off. So it's a hot torch, but it's I don't know.
It's like,
it's fun to handle.
It's about 1000 Celsius actually.
Because glass melts at what?
If you ask me, so it has to be around about 1000 Celsius.
Yeah. It's fun once you get used to it, but
and the growth process, you will have to grow so many, you have to repeat the process many times, right? Because it doesn't work once. usually what was the highest number of times you repeated to successfully get something, like just a rough number?
Between my grad student and I don't know, like 10 or 20.
10 or 20? Oh.
I feel like I've done like a solid 10 myself just to test out all the different conditions to get
Right.
to see which one makes the best.
And is there any elements, so we have to, for the general audience, we have to buy these individual elements from usually different companies and then make materials ourselves. So the hard part, were there any expensive materials in there?
I don't think so.
I don't think you don't think so. Yeah, that's
So
good
no
because
parties.
then you can make as many tries as you want, and the materials I work with are very expensive. So I have a limit on how aggressively can I work in the lab. So
Yttrium oxide's under $100. It was like 77.
it's still cheap, right?
Yeah.
Yeah,
It's
yeah,
not like
that's a
what
good
you and
one.
Mira do.
Yeah,
at
it's
all.
not like
So we have
European.
that going for us, I guess.
So that's the challenging part. That's a good part that you have cheap materials.
Yeah.
And you can do as many tries as you want.
Yeah, that's
good.
nice.
You're accepted into a grad school in Brown, right? Congratulations on that part. And do you have any plans for that? I'm sure you're excited, but is there any particular research stream you want to move in?
I'm not sure. For now, I want to stay in condensed matter experiment. I think it was a really natural transition for me, and it's a field I really enjoy getting to know. But I'm excited just to be curious about the world again and see all that physics has to offer.
Yeah, and so you'll be still staying in condensed matter.
Yeah, I think so.
Oh, that's
yeah,
great.
I don't.
That's awesome.
I always joke with people, if you send me to CERN next year,
Uh,
I could be a high energy experimentalist, but
but yeah, that's the deal.
that's not going to happen. So.
Awesome. Thank you, Suleiman. Thank you, Grace, for being here. Congratulations on going to graduate school and graduating from BC. And thank you, everyone, for joining in. We will see you next time.